Our next speaker is Michel Devoret, born 1953 in Paris, France. He received his PhD in 1982 from Marseille University, as you heard in a few seconds ago. He's now professor at Yale University, New Haven, also at Santa Barbara, UC California, and is also at Google Quantum AI USA. So please join me in welcoming Michel Devoret to the stage.
Thank you. Good morning. It is a great honor to give this lecture in front of distinguished colleagues and friends, and also my close family. I would like also to thank the Swedish Academy of Science and the Nobel Foundation for this prestigious award. I feel actually doubly honored because, as you know, this is the 100th anniversary of quantum mechanics. Quantum mechanics is counterintuitive. Its logic is very different from the logic we experience in our everyday life. When I started my PhD, I actually applied quantum mechanics to a simple molecule, the hydrogen molecule. But like this character that you see on the right of this slide, my life took a new turn when I did a postdoc in John Clarke's lab 40 years ago. And with John Martinis, who was a graduate student at the time, and John, we started an experiment that was a test of how variables like currents and voltage, how does quantum mechanics work for these variables. And for me, this was a lucky break. I had dreamed for many years to work on the foundations of quantum mechanics. I was inspired by the work of Alain Aspect, who defended, and I had the pleasure of being there in the audience when he defended his thesis in the mid-70s, and the room was packed. So quantum mechanics at the macroscopic scale is not something that was completely new at the time of our experiment. Actually, you could hear about it in popular books that try to convey quantum mechanics to a large audience. But this quantum mechanics at the macroscopic scale was essentially in the form of thought experiment. And here I'm going to give you an example which was invented by George Gamow, who wrote this wonderful book, Mr. Tompkins Explores the Atom. So George Gamow actually, very quickly after the discovery of quantum mechanics, explained alpha decay, alpha radioactivity, by considering the following idea. So on the left of the slide, there's a reminder that tells you what is radioactive alpha decay. If you take, for instance, the atom of uranium, and you consider its nucleus, after a certain time, it's going to decay into thorium and emit an alpha particle, which is actually a helium atom, or something you can describe also as 2 protons and 2 neutrons. So this alpha particle is, in the words of Gamow, it is transposed into a marble on the diagram on the right. And this marble starts in a sort of molehill with a crater in the middle. And when the marble is at rest, classically, it cannot escape. Its escape would mean that energy would not be conserved. You have a hill to go up and down to escape. But quantum mechanically, this marble can borrow energy. Can borrow energy from what I would call the Planck bank, which specifies that you can borrow a certain amount of energy during a small amount of time. Actually, this is given by the Planck's constant, and this Planck constant tells you that you can borrow during 1 second 10 minus 34 joules, or during 1 nanosecond, 10 to the minus 25 joules. And we're going to see that 10 to the minus 25 joule is actually a manageable quantity. So this particle escapes, and why does it escape? Well, the crater corresponds to the attractive interaction of the alpha particle inside the nucleus due to the strong force. So this is why you have a dip. But outside, the alpha particle, which is charged positively, is repelled by the nucleus and hence the downward slope. And so this potential is the description by Gamow of alpha decay. And you see that Gamow, in fact, has no doubt if the marble would be sufficiently light, well, you should observe this effect. If you take a dog bowl at home and a marble, you should see this, provided, of course, that the marble is sufficiently light. Now, Tony Leggett, in the mid-80s, says, wait a minute, actually, we have absolutely no evidence that quantum mechanics works at the macroscopic scale of marbles. In fact, Tony Leggett was well placed to say that, because even though people at the time were saying that superfluidity or superconductivity are phenomena that display quantum mechanics on the macroscopic scale, in fact, he knew that in such phenomena, quantum correlations are actually deployed on a very small scale, and the order propagates at the macroscopic scale by completely classical interactions. So Tony Leggett is essentially proposing experimentalists to try to see if you can make a cat in the superposition of being dead and alive at the same time. And in proposing this to experimentalists, he is really interested in measurements. What happened in a measurement when the superposition is actually changing, the measurement is changing an AND into an OR. You have only one outcome. The cat is either dead or alive when you make a measurement. Now, of course, Tony Leggett had a very special cat in mind. Instead of taking a live cat, he was thinking about an electrical circuit. And on this picture, what you have is an oscillator, an electrical oscillator, which actually you have in your cell phone. It's made of aluminum. It's millimeter in size. And if you cool it to 20 millikelvin, which was the temperature of our experiment, all the electrons in this circuit are condensed and form one incompressible fluid that is going to move bodily in the circuit. To understand this idea of macroscopicness of the circuit, it's good to compare it to an atom. So I'm going to take a very simple atom, the hydrogen atom, and you have an electron which orbits around a proton there. And on the right, you have the equivalent system, but of course the dimensions are many, many orders of magnitude larger. You have this electrical circuit, which is a coil, an inductor shunted by a capacitor. And in that system, the electrons are going to move bodily from one plate of the capacitor to the other. So let's see what this motion is. This is okay. So you see the electron classically, of course, in a classical picture, orbits around the proton. And what is happening in the circuit? So you see in the circuit, this whole incompressible fluid moves from one capacitor plate to the other by passing through the inductor. But at this low temperature, as you can see, suggested in this animation, there's no internal degree of freedom that is actually stimulated by this motion. So there's actually an analogy that you can draw. In the atom, you have a single electron. In the circuit, you have a whole superconducting condensate. And if you want, it is the center of mass of this condensate which is the analog of the position of the electron. The velocity of the electron is the current through the inductor, and the force on the electron, if you want to push the analogy, it would be the voltage on the capacitor. Okay. Now, there's a big difference, of course, and why do we say that this circuit is macroscopic? Well, from an application point of view, you can attach wires to a circuit, and therefore you can make two circuits, for instance, interact very strongly, or you can make a very strong measurement on the circuit, which is much more difficult to do on the atom. So that's why we are interested in demonstrating quantum mechanics at the level of circuit. Now, we have to test if this macroscopic object is really quantum. And Tony Leggett's hypothesis was that you could take the flux through the inductor of this circuit and consider it as a position, and the charge on the capacitor is the conjugate variable and can correspond to the momentum of a particle. And therefore, if you follow this idea, which is the equation in the bottom, then you expect that there will be quantized energy levels, as John mentioned in his talk. But this will happen essentially in any circuit. In the case of this inductor and capacitor, you have actually equidistant energy levels. What is really different from an atom in this circuit is that, for instance, if you take the transition frequency between levels, this transition frequency, as you can see in the formula that I have indicated on the right, this is determined by these two ingenerable quantities, which are the value of the inductance and the value of the capacitance, which you can change by changing the geometry. You cannot do this for actual atoms. You have 92 atoms in the periodic table, and that's it. Or if you want, the equivalent of the L and the C here are fundamental constants that, like the electron charge and the mass, which are given once and for all. Here we can adapt the circuit to a particular function we are interested in. Now, macroscopic objects are submitted to a lot of friction in general. And for instance, in an electrical circuit, you may have some resistance across the capacitance and the inductance, and this has the effect of broadening the energy levels. And as you can imagine, if the dissipation is too large, the levels will be too broad, and all this quantization will disappear because the levels will overlap. So you have to be careful in controlling the dissipation. Can we can we take this circuit and put it in a quantum state? Yes, we can. We can actually use some residual dissipation. So dissipation is not completely bad. You need a little bit of it. And with this, you can reset the circuit, provided that the temperature of this dissipation is low enough. And the equation that John mentioned already is that the transition between levels, the energy between two consecutive levels, has to be greater than actually the energy of temperature fluctuation. And so you can see that for a circuit that you have in your cell phone, which is at a few gigahertz, in fact, H bar is not really that small if you have a dilution refrigerator, which really cools the resistance to a few tens of millikelvin. Okay, but at this point, Tony realized that there was really a problem. In fact, this LC circuit is a little bit too simple. It's when you stimulate it with some microwave radiation, what happens is that because all these levels are equidistant, you will stimulate all the transitions at the same time. And in fact, if you start from the ground state, you will end up with a state whose average will behave in a completely classical way. So this is a problem. So we say, it is said in quantum mechanics textbook that the harmonic oscillator is always in the correspondence limit. 40 years ago, this really was a problem. Today, there are ways of going around this. But you see, what we need is actually not a system with a parabolic potential, where transitions are degenerate. We need a system where the potential energy is anything but a parabola. The parabola is in dashed line in this diagram. You don't want that parabola. You want any potential that would flare up, for instance, as you go up in energy. In that case, all the transitions now are non-degenerate, and if, for instance, if you have this circuit at high temperature which emits radiation, it will emit this radiation in discrete lines. And so you can address now each transition separately. So if you shine microwave at a particular transition, you can go, for instance, from 0 to 1, from 1 to 2, and in this way address any quantum state. Now, there is something that really will determine how good will be the quality of your manipulation. You see, if you want to control this system, to manipulate it, there is something very important that you have to observe. You want nonlinearity, you want these lines to be separated, but friction is important, because what counts is the relative distance of two transitions relative to the width. So you need to have a good nonlinear system, but you also you need very small dissipation. And this was something that Tony Leggett realized. There is only one electrical element that provides this combination of very low dissipation. In fact, there's no known limit to the dissipation of a Josephson tunnel element, and enough nonlinearity. So, what does this junction, how you should think about this junction? You see in the schematic on the right of this picture here, I have represented the Josephson tunnel element, which replaces the inductor, by a cross. And the cross doesn't evoke at all an inductance, but the cross was chosen for historical reason. And if you've If you follow John's talk, it should be pretty obvious why it should be a cross, but I won't go into this detail. Let's take this cross element, this Josephson tunnel element, and relate the current to a sort of flux. So this is what is called a generalized flux. You remember Faraday's law. The time derivative of a flux is a voltage. We can invert this relation and introduce the time integral of the voltage across the junction. And that creates a variable which is the equivalent of a flux. Now, if we... okay, so... okay, good. If we now plot the energy of this tunnel element as a function of this generalized flux, we do get something that deviates from a parabola. In fact, it deviates a lot. We get this cosine potential. And this cosine potential has a periodicity which is given by h bar over 2e. And why does E come into play here? It's because electrons tunnel one at a time across the junction. In the superconducting state, they tunnel as pairs, but what is important, what determines the shape of this potential, the periodicity, is the fact that charges goes one by one through the junction. Okay. Now, you see, in this potential, you will have non-equidistant energy levels, but of course, the fact that the potential is flat like this makes things actually quite difficult to measure. Actually, we could have done a specific heat measurement and resolve these levels, but this was 40 years ago, an extremely difficult experiment. So instead, what we do is that or what we have done was to pass a bias current. So we have this current generator which passes a current through the junction, and this has the effect of tilting this cosine potential. Now, we have these levels, but they are metastable. If you populate one level, it will eventually decay because its wave function leaks into the barrier. There are two parameters that determine this potential, two very important parameters. There are this plasma frequency, omega sub p, which is the frequency of the small oscillations at the bottom of the well, and then there's this barrier height. It is absolutely crucial in the experiment to control these two parameters. And why? It's because actually there are two escape mechanisms. The state of the circuit, which is represented by this yellow ball here in the diagram, so that's the whole state of the circuit, it can escape from this well in two possible processes. The yellow process is a process in which the thermal excitation is going to help you go from one level to the next and so on until you go out of the barrier by the top. If you are in the regime where the temperature is sufficiently small and the crossover temperature is given by this ratio of the energy separation divided by K Boltzmann, then you will escape through the barrier by the tunneling corresponding to the purple arrow. And I hope that you recognize that the situation is similar to alpha decay. So our whole circuit is now the equivalent of a radioactive nucleus. How do we detect this, that, you know, the equivalent of radioactivity? Well, in this system, you see the whole state of the circuit changes. So on the left, the current, this bias current, can go through the tunnel element, through the cross, and that corresponds to this yellow particle, which corresponds to the state of the circuit. The particle is trapped. It can move in the well, but its average velocity is 0. That means that across the circuit, the voltage is 0. This is the 0 voltage state. You see that on the diagram, you have a resistance, and this resistance actually is something that we impose in the circuit. It corresponds to the voltmeter. The voltmeter is going to be the equivalent of the Geiger counter in radioactive decay. When the whole state of the circuit switches from the 0 voltage state to the non-zero voltage state, or in the slide here, it's just called the voltage state. There's a voltage that appears across the circuit, and we can detect it with our voltmeter. And why do we produce a voltage? Well, you see, as soon as the particle escapes, it rolls down this tilted potential, it picks up speed, and speed in our language is voltage. So by detecting this pulse of voltage, we know that the whole circuit has changed state. And this is the equivalent, the macroscopic equivalent of alpha decay. Now, I have to say something very important. There is two tunneling in this experiment. There is tunneling at the level of single electrons that go through the barrier, and that creates the Josephson effect. It creates the shape of the potential. And this tunneling has nothing to do with the switching of the entire circuit from one configuration of the currents into another. These two levels should not be confused. What we have discovered is that it's the tunneling of the state of the whole circuit, the tunneling of electrons and the tunneling of electrons in pair. That was the discovery of Josephson. So what we've done is post-Josephson physics. Okay. Now, John has shown a photo of our experiment. In this yellow box, we show exactly the shape of the junction. It's a junction that is actually lead indium junction, niobium lead junction, which has the merit of being superconducting at helium temperature, so we could check all the parameters in situ. These cylinders are actually filters, and they are very important, as John said. In this experiment, we narrow the bandwidth to kilohertz, and we have to filter out every other part of the spectrum. As I said, it was important to measure all the parameters of the system in situ. And in particular, this plasma frequency is very important to measure because it determines the crossover temperature. And an experiment that we did in the classical regime taught us that we could, if we measured the enhancement of tunneling, find this plasma frequency on the right edge of this resonance curve. And John has described our experiment. He has described our two papers. I'm not going to, in view of the time, I'm not going to repeat what he said. I will I think it's important to mention that 14 years later, colleagues at NEC, Yasunobu Nakamura, Yuri Pashkin, and Zhou Shen Tsai, saw this superposition of the first and excited state, not in frequency domain, but in the time domain by doing this beautiful experiment on Rabi oscillation in the Cooper pair box. And Yasu is here in the audience, and it's great. On the right, so a few years later, we showed at Saclay that we could control this qubit not only on one axis, but on all axes. And you see also that the time scale is 3 orders of magnitude larger here. So coherence had been increased. Well, at this point, I am almost done. I see that I only have a few minutes left. So in that last few minutes, I just want to tell you that these previous experiments launched this new field of quantum superconducting circuits in which you have these 3 elements which can be combined to make artificial atoms, molecules, and even more complex circuits like quantum limited amplifiers. And I would like to acknowledge here all the people who are in the audience that have participated in this exploration. These artificial atoms have this analog of the Mendeleev table. I don't have time to comment, but each of these dots represent some configuration, some kind of new artificial atom. And there are 2 that are popular, the transmon and the fluxonium. And recently, by the way, this is an image of the transmon. And recently, I will have to rush here, but in the group of Nathalie de Leon and Andrew Hook at Princeton, the quality of these artificial atoms has been extended to a number which is basically that of the hydrogen atom. And what can you do with these artificial atoms? Well, you can do a certain number of experiments you cannot do with real atoms, and this is a list of these experiments. And finally, I would like to just say that this, as a perspective, this new field of artificial atomic physics and microwave quantum optics open new applications in quantum information processing and quantum sensing. And the question that is left is where can we extend, at what point can we extend quantum mechanics to macroscopic systems? This is still an ongoing question, even though we've pushed the scale at another level. And finally, since I have 0 minutes left, I would like to acknowledge all my colleagues with whom I have had this great privilege and great happiness in exploring these superconducting circuits over the last 40 years. And on this, I would like to thank you for your attention.